Hello everyone, welcome to our video solution to problem 4 from Superquiz 2. In this problem, we're told that there is some wire lying along a helix, the helix is given by this parameterization function. And we want to find the mass of the wire, which is made more complicated by the fact that it doesn't have a constant density. And we know that because there's a density function given here. So depending on the x, y, z coordinates, the density is going to change. So the way we're going to compute this is by using a line integral. So let's give a name to this helix. Let's just call it C. And the mass, well, the way you can think about it, right? Okay, you have this helix, right, heading up. Of course, these circles should all be the same size, but well, okay, can't draw very well. And if this was a constant density, then you would just take whatever that constant density was and multiply it by the length. Now, because it's not a constant density, what we can do is sample along this curve. We can sample the density function, assume it's constant on some arc, and then multiply that density by the length of the arc, which, well, sometimes they call it ds, or I like to call it dc. Okay, of course, ds is going to win out because that goes back to Riemann. All right, and then what you would do is just add up all of these approximations, right, given by sampling rho on that curve at some point, multiplying by the length, and you'd go until you got to 4 pi, which, right, that should be like 1 rotation and then 2 rotations, right? So we don't need all this stuff up here, right? We can cut it off. Okay. So the mass then, we're just going to get by then taking the limit as the number of these little intervals goes to infinity and the size of them goes to 0. That is, we're going to compute an integral. Okay, and so we're just going to multiply the density function by the length of these little arcs, which we can call dc or ds. All right, so to convert this into a single variable integral, we're going to work left to right. So first, normally we would have to take this curve and parameterize it, but that's already been done for us. And we can see that the bounds or the domain for t will be between 0 and 4 pi. All right, next we have this function rho, the density function, and we only want to evaluate it on the helix itself. And we know that on the helix, the x-coordinate is given by cosine of t, the y-coordinate by sine of t, and the z-coordinate by t. So rho evaluated at some point x comma y is actually going to be, well, we know x, y, z plus 1, but we can actually write it as cosine of t times sine of t times t plus 1. So we have cosine of t, sine of t, t plus 1. And now we need the dc. So the dc, that's given by the square root of x prime of t squared plus y prime of t squared plus z prime of t squared, and then times dt. Okay, so this is just coming from the Pythagorean theorem, essentially. In our case, the derivative of x, we're talking about the x component of the curve, right? That's what we actually care about, right? dc is explicitly talking about the curve. That's why I like using the c. The derivative of cosine is negative sine, and so when you square it, you end up with sine squared. Y prime, well, the derivative of sine is cosine, so we get cosine squared. And then the derivative of t is 1, so we'll just get plus 1 squared, which is 1, and then all times dt. And of course, sine squared plus cosine squared is 1, and so we end up with the square root of 2 dt is equal to our dc. So this square root of 2 can just come out to the front, and then we can write a dt. All right, so now the problem is just reduced to this calc 1/calc 2 single variable integral. So this one I'm going to solve by just using a nice identity on this bit. So cosine times sine. So cosine times sine is just a half sine of 2t. So that simplifies matters a little bit. I still have this t to worry about, and I can handle that by using a little integration by parts. So let's do this integration by parts on the side. I like to use the tabular method. So we have t, and we have 1/2 sine of 2t. I'm going to differentiate the t until I get 0, and then I'll anti-differentiate just as many times. So I'm going to get negative 1/4 cosine of 2t, and then negative 1/8 sine of 2t. I can connect with a plus and a minus, and reading along these will give me an antiderivative. All right, so I have the square root of 2 times, all right, now I actually can break this up right into two different integrals. So let me just quickly split those up. So we have 1/2 sine of 2t times t dt plus the integral from 0 to 4 pi of, well, this is just a 1, so that's just a dt. And this guy is really easy because you're just integrating the line segment 1. So you just get the length. So the length of that interval is 4 pi. All right, so this is the one that we're really interested in. So let's see here. We're going to get the square root of 2 times. All right, we found an antiderivative. It's going to be negative 1/4 t cosine of 2t. So negative 1/4 t cosine of 2t. Minus minus is plus 1/8 sine of 2t. And we're going to evaluate that between 0 and 4 pi, and then we still have this plus 4 pi. Okay, so let's see. We have the square root of 2 times. Now, at 4 pi, cosine of 2t, that'll become cosine of 8 pi, which is just 1. So I'm going to get negative 1/4 of 4 pi. Okay, well, negative 1/4 of 4 pi is going to be negative pi. Okay, now what about sine of 8 pi? Well, that's 0, so I don't get anything there. All right, now I'm going to subtract, and what happens when t is 0? Well, cosine of 0 is still 1, but now the t is also 0. So I seem to have a 0, and then, oh, look, sine of 0, that's also 0. So actually, there's nothing even to subtract. So I'm going to end up with root 2 times negative pi plus 4 pi. Of course, 4 pi minus pi is 3 pi, times root 2 is 3 pi times the square root of 2. And that is the mass of the wire.